the mask bit is 0, the interrupt is available. If the mask bit is 1, the interrupt is masked. Bit 3, mask set enable MSE, is an enable for setting the mask. If this bit is 0, the mask is ignored and old setting remains. If it is 1, then new settings are applied. Bit 4 of the accumulator in the sim instruction allows explicitly resetting the RST 7.5 memory even if microprocessor did not respond to it. So, this is only particularly for RST 7.5 to enable or disable it. Bit 5 is not used. Bit number 6 and bit number 7 is used for extra functionality such as serial data transmission. There is an example of for sim instruction. Set the interrupt mask so that RST 7.5 is enabled and 6.5 and 7.5 are 6.5 is masked and 7.5 is also enabled. So, we have to enable 5.5 and 7.5 whereas 6.5 is masked. So, bit number 0 is 0 enabling 5.5, bit number 1 is 1 disabling 6.5, bit number 2 is 0 enabling 7.5, bit number 3 MSE is 1. Do not reset the flip flop, bit number 4 is 0, other bits are not used, so these are 0. We get 0 0 0 and 1 0 1 0, that is 0A. EI means enable interrupts. So, first of all the interrupts are enabled. Then MBI A 0A, 0A is shifted to accumulator, then sim. After doing sim, this bit pattern is applied to interrupt system. So, automatically 5.5 and 7.5 interrupts are enabled whereas RST 6.5 is masked. Apart from this triggering levels, as we seen in the last interrupt diagram, there are the triggering, these are the inputs which are applied to the interrupts, that these are the triggering levels. So, RST 7.5 is positive edge sensitive. So, when a positive edge means when we are going from 0 to 1 appears on the RST 7.5 line, a logic 1 is stored in the flip flop as a pending interrupt. Since the value has been stored in the flip flop, the line does not have to be high. So, there is only an edge, it becomes high and this high is stored in the flip flop. So, whenever the microprocessor checks the status, it must be recognized. The line must go to 0 and back to 1 for a new interrupt to be recognized. So, there is always a positive edge, as means when we are going from 0 to 1 to enable this to on this interrupt 7.5, and this 1 is stored in the its enable flip flop in its particular flip flop as a pending interrupt. So, it does not have the value does not have to remain high, but for a new interrupt again this value must go to 0 and then to 1. Whereas, RST 6.5 and RST 5.5 are level sensitive, as 7.5 is a positive edge sensitive, these two interrupts are level sensitive. That means, the interrupting signal must remain high 1 until the microprocessor checks for interrupts. There is a difference between these two systems, whereas 7.5 must not to be remain high. It is only from 0 to 1 and this high this level is this 1 is stored in the flip flop as a pending interrupt. Whereas, in case of 6.5 and 5.5, their high level remains stored present, always present whenever the microprocessor checks for these interrupts. Trap is the only non-maskable interrupt. It does not need to be enabled because it cannot be disabled. It is the highest priority among interrupts. It is edge and level sensitive. So, it is having both triggering levels, edge as well as level. That means, it must make a low to high transition, that is 0 to 1, and remain high to be acknowledged. After acknowledgement, it is not recognized until it goes low, then high again and remains high. So, to make it enable again, it is a positive edge triggered as well as level triggered. Trap is used for emergency systems, that is it is used to avoid this so that means the edge as well as level triggering is used to avoid fast triggering due to noise and logic glitches. Trap is usually used for power failure and emergency shut off. When the 8085 is reset, its interrupt enable flip flop is reset. That means all the interrupts are all the maskable interrupts are disabled. So, the only interrupt that is available during reset condition is a trap. Trap is a vectored interrupt and its vectored address is 0024. So, in case of bus ideal machine cycle, in case of these four interrupts, RST internal, that is vector address is generated internally, PCH and PCL goes to stack pointer, and program counter starts from a new address that is given by the microprocessor. Non-vector interrupt, INTR is the only non-vector interrupt in case of 8085. The interrupt process should be enabled using the EI flip flop, EI instruction. The microprocessor checks for an interrupt during the execution of each instruction. If INTR line is high, microprocessor completes current execution, disable the interrupt and sends INTA bar, that is interrupt acknowledge signal, to the device from where it gets the interrupt signal. When the external device gets INTA signal, this device sends a RST code to the microprocessor through data bus. Upon receiving the INTA signal, microprocessor saves the memory location of next instruction on the stack and the program is transferred to a particular call location specified by the RST instruction, which is supplied by the external device to microprocessor. So, in case of INTR, the RST address, the vectored address is supplied by the external device to microprocessor, whereas in case of all other interrupts, the address is already known. Then microprocessor performs the ISR. ISR must include the EI instruction to enable the interrupts again, and at the end of this ISR there is an instruction return RET, which retrieves the address from stack to the program counter, and program is again transferred back to where the program was interrupted. Although INTR is maskable interrupt, but it is masked only using instruction EI or DI. It does not need a instruction SIM to get enabled, just instruction EI is enough. There are 8 restart instructions in case of 8085, that is RST 0 to RST 7. So, in case of INTR, 8 devices can be interrupted at a time. This is RST 0 to RST 7. These all are having 8 their fixed addresses. The calculation is again simple by multiplying 8 with this RST value, then convert it into the binary and hexadecimal. The restart sequence is made up of 3 machine cycles. In the first machine cycle, microprocessor sends INTA signal. While INTA signal is active, microprocessor reads the data lines because it expects to receive RST code from the interrupting device. In second and third machine cycle, the 16-bit address of the next instruction is saved on the stack. So, there are 3 machine cycles in case of INTR restart sequence. First is it gets a INTA instruction signal, then in second and third machine cycle it saves the current contents of program counter into stack. Then microprocessor jumps to a particular RST instruction. There are 3 different RST instructions in this case. This is the example for RST 5. So, we get this is a microprocessor, it gets a code 80 to 87, get this opcode EF from this external device, and EF represents the RST 5. During interrupt acknowledge machine cycle, the microprocessor activates INTA. This signal will enable the tri-state buffer. Then microprocessor will place EF opcode on the data bus and microprocessor jumps to 0028. This shows the interrupt acknowledge cycle. INTR interrupt is checked by the microprocessor in the last machine cycle of the last T states of each instruction. The INTR line must be deactivated before the EI is executed, otherwise the microprocessor will again be interrupted again. Once the microprocessor responds to INTR, it sends INTA bar signal, and then it gets a opcode from the data bus, from the external device through data bus, and it goes to particular RST. There is an external device, that is PIC, programmable interrupt controller, that functions as an overall manager in case of interrupt system driven system environment. It accepts requests from the peripheral equipment, determines which one of these is of the highest priority. 8259 is a particular PIC, programmable interrupt controller, is used for this interrupt driven microprocessor system. It manages 8 levels or requests at a time, which can be expanded up to 64 levels. It is programmed by the system software as an I/O peripheral. Each peripheral device usually has a special program or routine that is associated with this specific functional or operational requirement, that is known as a ISR, interrupt service routine. The PIC, after issuing an interrupt to the CPU, must somehow input information onto the CPU that can point the program counter to that particular service routine associated. This particular address is in the vector table IVT and will often be referred to in this document as a vectoring data. So, this is a device 8259 that can have 8 interrupt requests at a time, but the interrupt request which is having highest priority can be handled. Through this we get an RST code through this lines 80 to 87, and microprocessor jumps to that particular ISR address. Pending interrupts. Since the 8085 has 5 interrupt lines and interrupts may occur during an ISR and remain pending. So, using the RIM instruction we can check the status of pending interrupts. There is a bit pattern of instruction RIM through which we can check which interrupt is masked or not unmasked, or which interrupt is currently pending or not pending. So, first 3 bits are used for to check the whether masking is done or not. Third bit is for EI, interrupt enable flip flop. Next 3 bits 4, 5 and 6 is tells whether particular interrupt is pending or not, and bit number 7 is used for serial input data, that is extra functionality. So, first 3 bits are for checking the whether these 3 interrupts are masked or non masked, that is 5.5, 6.5 and 7.5. Third bit is for interrupt enable flip flop, and 4.5 and 6 number bit is to check whether the interrupt is pending or not. So, bit 0 to shows whether the interrupt is masked or not. Bit number 3 is to enable the interrupt enable flip flop. Bit number 4 to 6 show whether or not there are pending interrupts 7.5, 6.5 and 5.5. Microprocessor can be interrupted again before the completion of ISR, but there is a for multiple interrupts there is an priority system which tells which interrupt is to be handled first. So, the solution is for the priority system is a priority encoder, as there are many interrupts which can handle at a time. By default 8085 has an internal established fixed priority, according to which trap is the highest priority, then 7.5, RST 6.5, RST 5.5 and INTR. So, last there is a summary of this interrupt system. INTR, this is maskable, it is enabled or disabled by instruction DI, it is vectored, it is not vector interrupt and it is level sensitive, whereas 5.5, 6.5 are maskable. These are enabled disabled by EI, DI and SIM also. It is vectored, so it is also level sensitive. 7.5 is maskable, it is enabled disabled by EI, DI and SIM instruction. It is vectored and it is edge sensitive, whereas trap is a non maskable, so it cannot be masked. It is vectored, it is level as well as edge sensitive. Thank you.